hear voices.
Hello, good morning, good afternoon, good evening, everybody, wherever it might be. It is my great pleasure to welcome my old friend and colleague, sorry, old in the sense that we know each other for a long time, TOMASZ BRZEZISKI, my most favorite Welshman from Białystok. And he will tell us about Hopf Heaps and Hopf Algebras of translations. So I understand we'll be translating from Welsh to Polish and back.
Thank you, Piotr.
It's a pleasure to have you, Tomek. It's all yours. Take it away.
Prynhawn Hopf. Okay, is it okay?
Nice to see you.
Bravo potimaeto. Okay, sorry. That's all the Welsh that will be there. But since Piotr announced my talk with the university name given in Welsh, I thought I was expected to give a talk in Welsh.
No.
Maybe not. Maybe not.
English is fine. Let's be boring and old-fashioned.
Right. So thank you very much, Piotr, for your invitation. Indeed, we are old friends in both all possible senses of the word. And are good friends, and a good friend is a person who relieves you from some duties. And when you go to a seminar, usually people give you a slot. But Piotr is so kind that he gave me a title. I talk. So I didn't have to think for a second what I will be talking about. Okay, so I will be talking about Hopf Heaps and Hopf Algebras of translations. This is a joint work with my colleague from Białystok, Małgorzata Kryniewicka. And it's an attempt to, in a sense, dualize, in a sense, reformulate, and also discover some new things by doing this reformulation and dualization of something which is known as quantum torsors. And I will say a few words about what they are and how they appeared. Maybe not so much as what they are. I will give you the definition which I will be using in this talk. And quantum torsor is a sort of quantized version of quantum groups, or algebras, are quantum versions of linearized version of groups. Quantum torsors are linearized and dualized versions of something which is known as a heap. Okay, and this year we are celebrating the centenary of Heaps. So I will explain on a few minutes what a heap is. Okay, so heaps were introduced by Prifysgol, and Prifysgol introduced the heaps.
Sorry, one result is from the future, 2029, right?
Well, I can think like this, yeah. Maybe I should already put 19 or 9 at least at France to avoid the confusion. So this shows the. No, this is highlighting. You have to tell me how I do this.
Yeah, for highlighting, yes.
Perfect. Okay. Right. So a heap is a set. In general, it doesn't have to be occupied by anything. It could be an empty set. Together with a ternary operation, and I will use this notation, this bracket notation, which satisfies 2 conditions or 3 conditions, depending on how you count them. And I don't mean whether you count from 0 or from 1, but as you will see, a couple conditions which come under one name. But anyway, the first condition is an associativity condition. Now, what is important to note here is that we can apply the operation twice and move a bracket within the bracket by 2 places, not just by 1 place. So it's a sort of, sometimes people say it's a heap associativity or weak associativity or quasi-associativity. Okay, so this is an associative law for heaps. And the second condition tells us that if 2 guys meet, then we recover the third one. Okay, so these conditions are known as Marzev identities. In particular, they imply that heap is well, the heap operation is an idempotent operation. So if you put A2 3 times, you get A2. Right. Prifysgol originally introduced abelian heaps. He didn't call them abelian, he just called them heaps, and then Pear gave the definition that I give here, A and B. So a heap is abelian if we can read the words forwards and backwards inside the brackets and get the same answer. Okay, so that's a sort of commutativity. There is this pivot in the middle, which does not change when we commute C with A, the outer inputs. Now, the one thing that one can observe already at this stage, this is a non-trivial exercise, it becomes trivial if we connect heaps with groups, is that there is a version of, you can shift by one here, the bracket, but then you have to reorder A2, A3, A4. So if you shift by one, the order of elements would be A1, A4, A2, A3, and B. And actually, it was on the slide. Okay, so as I say, it's a non-trivial exercise. I don't remember what I gave. It's the next step, right? So there is a close relation between heaps and groups, and that's actually why they were introduced under the name. So the original name was Herd, and they appeared, which is Char. And at some point I attempted to use the German, I don't know what, is it D, there, or das, Char? If I wrong, which one is that?
D sharp.
D sharp. Okay, so I used the wrong one, and the audience was Uli Krager, who shouted at me, and then since then he laughs at me. The D sharp, which indeed translates as a sort of herd or flock.
Yeah.
It has also some bad connotations, but let's forget. Anyway, so there is a relation between heaps and groups. Namely, whenever you have a group, then you can make this Turner operation, which combines group operation and the inverse. So I write this everything in the additive notation, but you can think about this as a non-commutative operation. So A minus B would be A inverse. And if you realize this, then you can, well, actually you can, what you can realize next is, let me see if I can say this, so I don't say it, I will say it later on. If you fix the middle term here, then you can reduce the operation, you fix an input here, provided you have non-empty set, of course, because otherwise there is nothing to use to fix the middle term. Then you have a binary operation. And this binary operation becomes a group operation. Okay, so there is a, whenever you have a, so a heap is in a way a heap of groups. You pick an element, and this process is called retract. So you take the retract of a given element, you get a group. For each element, you get a group. They are different groups, but they are isomorphic to each other. So we can think about a heap as a sort of, well, heap of groups. Okay, every element or a bundle of groups.
So I know it's a stupid question, but how does it differ from a groupoid?
Well, it does differ from the groupoid, because in the groupoid you have well,
Units.
yes.
Mm-hmm.
We don't have them here, at least at the level of
the level of definition.
May I continue?
Yeah, sure.
Mark, why your first example is an abelian group instead of, for instance, an affine space?
It's a serious question. So I will take off the jacket.
You have to roll up your sleeve to answer.
Because the group is an additional structure requiring a neutral element, as Piotr asked.
So, Tomek, to answer your question, I usually expect the audience not to read the slides beforehand. Okay, so the next example will come from a fine space. The prophet. So I know if you have a prophet in the audience, then it's anyway, so there is a connection on this level, what you can show, and this was shown by Jeremiah Certain in 1940s, is that if you have a group and the subgroup, take any coset with respect to the subgroup, normal, not normal, doesn't matter. The coset will have a structure of it. And this suggests that there is some sort of affine version that's like a vector space and the subspace, well, codimension one, and then you take the.
So in other words, you are speaking about orbits.
Yes.
In other words, yes.
That's why it's about groupoids.
Okay, so another notion which is sort of obvious, the definition of a homomorphism. So it's a function that involves sets which preserves the operations in the usual sense. Okay, so Tomek, pay attention now. Yeah, I'm satisfied. Yeah. Okay, so in an affine space, so what is an affine space? Well, in an affine space, usually the standard or classroom definition is that we have a affine space and the vector space, or the space of points and the vector space. And the vector space acts freely intransitively on the set of points. So what does it mean? It means that if we have any 2 points on the space, they will differ by a unique vector. So any 2 points we associate a unique vector. Any point can be shifted by a vector to a unique particular point. Okay, so you take a triple of points, you shift one by a vector between the second and the third one, and you end up in your space. And what you can also do, because we are so far I haven't really used multiplication by scalars here. So what we can do, we can encode the multiplication, but we can imagine the operation which take 2 points and the scalar and rescale a vector between these 2 points and add it to the origin of this vector. So you will get another vector. This is an operation which combines this addition point to a vector and rescaling of a vector. Now, the observation is that we can get rid of V altogether. So it's possible to give a definition of an affine space without referring to vector spaces at all. Okay, so an affine space is a heap. I should say abelian heap. Forgotten to write it. I know there are some people who say write abelian here just for the record, but it's an abelian heap. So all the heaps of which I will be talking will be abelian from now on. With an F action, and this is a ternary operation. So,
Sorry, what is an F? This is your field?
This is a field, over a field. F, you can define it over a commutative ring, and that's why I say F modules. So it's either commutative ring or commutative, well, or a field. For a space, you would have a field. Okay, and this is a ternary operation which takes a scalar and 2 elements in your heap and produces an element in the heap. Okay, which has the following properties. First of all, it is by heap operation. So what I mean by this, that if I fix the middle, which I will call the base for this operation, if I fix this base point, then and say fix this one, okay, keep this one fixed, then I have a map from F to A, and this has to be a heap homomorphism. While I see the the heap structure on F given by the addition and subtraction. So A minus or alpha minus beta plus gamma. Okay, so not a preservation of the binary operation, which is naturally given in F, but ternary combination of addition and subtraction. The next point is that this is associative, so this is not written very clearly. What I mean by this is that if I apply scalars twice and act under A and B, then it's like acting with the one scalar and then acting with another scalar with the same base A. Okay, so the base doesn't change. It's an action. Okay, I haven't said that if we fix the scalar, then again we have a endomap, which should be a heap.
Sorry, it's an action of what?
It's an action of a field. If you fix an A,
Yeah, but
then your field acts on the heap.
Yeah.
By heap. So the action is, well, if you like, you could write this as a homomorphism from F to the heap of the endomorphism of
ring homomorphism.
or the ring
Monoid homomorphism.
It's a monoid homomorphism, but also preserving ternary operations. So it's in fact, I don't want to use the word truss, but it's
Okay.
but this is the preserved monoid and the inbuilt ternary operation.
The naive question. So this action of the field on your heap doesn't make it a vector space?
No.
Because a heap doesn't have addition.
But there is a way of recovering vector space, and I will come back to this. Now, the third axiom, which we call it is called the change of base axiom, tells us that you are actually independent on this choice of the base. So if you don't like the point A, you can always change it to another point, let's call C, and we have a rule how to do it. Okay, so if I know how to act on C, then I can translate it to acting on A with the base A. And so it's a change of base axiom. And in the case of ring, commutative ring, not necessarily unital, well, I don't need to say anything more because I don't have any more structure to consider here. But in the case of fields or the unital ring, well, actually for the ring, we also have zeros of that. I should say how it behaves. But in particular, in the case of fields, we have two distinguished elements in F, 0 and 1. And 0 acting on whatever recovers the base, and 1 acting on whatever recovers the whatever. Okay. Well, this is just usual unitality. So combining this with that, you would say it's a monoid action.
So if in the line above I put lambda equal to 0, everything checks out because I have A on the left-hand side and I have CCA, but he told us that CCA is an A.
Okay, so if you want to put 0 here, right?
Yes.
Okay, so you have also 0 A. So you have A, then you will have CC, A,
which is A.
That is A.
Yeah, that's exactly what I said. Yes, sanity check.
Yeah. Thanks to Math's identities. Okay, so if you are a traditionalist in the case of traditionally taught what an affine space is, then what are the structures involved? Well, ABC is just this operation, translation by a vector from B to C of the element A, and the second operation is this scaled translation. Okay, so next, morphisms. So in the traditional language, morphisms are defined of affine spaces, are defined as functions. But actually it's a pair. So one determines, F determines this F hat, and this is a condition. So you can say, well, it's a function which induces a linear transformation between underlying spaces, which when applied to a vector, is the vector obtained by applying F to A and B.
So could you come back to this action? Yes, the last explicitly. This action is written as this. So this can be written in terms of the structure of an affine space.
Yes.
It's 1 minus lambda times A plus lambda times B.
Yeah, exactly. So it's
It's an
a fine
affine
combination.
combination.
Yeah, exactly. It's an affine combination. It's the only thing that if you think about it, you can write within the affine space.
Yeah,
I
but
don't want to mention.
my point is that the vector space is irrelevant here.
It is completely irrelevant. Okay,
Which is
so
funny because you started introducing this action of lambda in terms of action on vectors.
yes, because
Now we see that this action is well defined on the level of the affine space.
yes, without any reference.
Yes.
And there's a sanity check, right? I will come back how you recover the vector space. This is not a. Okay, so so on the level of affine spaces with this definition that I gave, you don't need any linear transformation. You just write the obvious from the universal algebra point of view notion of homomorphism. Okay, of course, F has to change the base as well, otherwise what written here wouldn't make sense. So everything has to be in B. Okay, so where is the vector space? Well, actually, there are a lot of vector spaces. They are all isomorphic. So in a sense, it reproduces the whole idea of the heap. Okay, so we've fixed an element in A, and I should also say that I said at the beginning that heap does not have to be populated by any elements, but from when I mentioned groups and affine spaces, I exclude all the empty set. I can include it and do the whole theorem with empty set, but it's an exceptional case which has to be treated separately every time. So it's better not to. I mean, do you believe in the existence of an empty set?
Yes, we do.
How can exist something which doesn't have anything in it? So it doesn't exist. Anyway,
Everything in mathematics is built with an empty set.
Exactly. That's the creation from nothing of something.
well, but not in the unique way. Anyway, this is not a philosophy lecture. Okay, so whenever we fix an element, then we have this retraction to the addition. So we have additive structure on A. So now I'm talking about specifically of the affine space defined.
But what you said is like a heap of groups, right? Because whatever element you have is.
Yes, but then, so we have the abelian group, but then using this special element, which I should mention, it's an identity, so it's a zero, that's why I call it O. O, it's a zero for this plus operation. I can, so now I have this distinguished element and I can define this, and this satisfies the axioms of the multiplication by scalars for a vector space. So,
Sorry, if you think about this action,
yes,
you always assume that your heap is abelian.
I always assume that the heap is abelian. One can do the theory with non-abelian heaps, I guess, but this is another thing. Okay, so what is the, so maybe I should say, what is the abelian heap condition for? So the abelian heap condition corresponds to the triangle equality in the definition of affine space. If you think about this geometrically, then the triangle axiom is precise, well, no, it's not precise, it's related to abelian. If you don't assume abelianness, that the action is heap commutative, so it's abelian heap, then you lose the triangle axiom in your structure. So I don't know what's, maybe it's relevant to non-Euclidean geometries. Okay, so we have a vector space, and what is the vector? Well, the vector is just, okay, so you see this vector here is written in terms of the heap operation. Okay, so if you want to use traditional definition, then you can fix your element, and this is how you can think about an affine space, right? You fix an affine space, it's a vector space with no specified origin. So you specify you take your favorite point, say this one, or maybe that one, and then you build your vector space out of this. Okay. Okay, so now there is a notion of a torsor related to abelian group and an abelian heap. Okay, so we have an abelian group, which I already mentioned. Whenever you have an abelian group, you can form it, or group, you can form a heap out of this. So this is a repetition of what was there. And now with such a structure, so I told you we can define a bunch of isomorphic groups. And but actually you can associate a unique group to a heap. And this unique group is the group of we call translations. So what you do, you define this map from A to A from your heap. And this is the definition. Okay, so C, the ternary operation, well, C goes into the first place, and then A and B written in that way. This is an homomorphism of heaps, and this is also an automorphism, because if the inverse of tau AB is tau BA, let's switch the indices, and you get the inverse. So it's an automorphism. But since you have automorphisms, what you can see, what you can also show that if you compose them, then this is closed under the composition. So it's a subgroup of the automorphism group of the heaps, which is closed under composition. So it becomes the subgroup, well, it becomes a group of itself. So it's a subgroup of automorphism of A. So we can define consider all such translations. And you see, this is independent of the choice of any element. I'm not constructing a bunch of groups, but just one single group, which sits in the automorphism of the heap. Okay, and in this way, we get a functor from heaps to groups.
And Tn stands for what?
Translations. Okay, so Tn is for translation. So these are it's a group of translations. Okay, so I wrote here how it acts on the morphism as well. The next thing here to observe is that this group acts freely and transitive on the heap. Okay, and this is precisely what people at some point in the 60s, I think they called it the torso. But here is the action. Okay, so the task that we set ourselves with Małgorzata was to try to adapt this picture.
Careful, because she's listening.
Okay, so I am careful. Okay. I sip water. Now I will start sweating. So the task that we set ourselves was to try to translate this picture as it is in the level of, well, the linearized version of this. So like groups, algebras, heaps, well, some sort of heaps. And to see what is the translations. Is this should be a Hopf algebra of translations, as you will see, there will be a Hopf algebra associated with Hopf heaps. Okay, so but of course we are not first to look at this, and the first person to look at this was Grunspan, who defined quantum torsors and cotorsors, and this was, well, the word quantum is maybe in this place I should stress it's not related to C-star algebras in this picture, but to the in the sense used by Drinfeld, so we just use it of algebra, particular Hopf algebra structures. It's purely algebraic. Now, then Peter Schauenburg, more or less at the same time, realized that quantum torsors correspond to something which he considered bi-Galois objects. I will explain later what it is. It's needed. Okay, and the Greenspan definition included a particular map. So it was sort of, there was ad hoc defined map which allowed us to, so I will come back to this and show where it enters, but essentially, when you look at this associativity of the heap operation, this by 2, then if you write it in the group form, then when you translate by 1, shift by 1, then there is a inverse entering, and you translate then again shifted by 1, then the inverse enters again, and this inverse is an involution, right? So you get back the original thing, but in the usual world of algebras, the antipode does not have to square to identity. So there is a certain map. And Greenspan proposed such a map built into the definition. This quasi-associativity, shifting by 1, will introduce some additional map. And Schauenburg, in the second paper, showed that actually you don't need to assume it. You can construct out of the axiom, so you can reduce the number of conditions.
It's kind of like canonical entwine, right?
Well, it's a sort of, you just realize Peter's papers are not published. They are on archive. Okay, so so I will tell you why. Okay, so when you see paper which is, or a couple of papers that are 20 years old, you start thinking, well, maybe there is something not quite right. But not with Peter Schauenburg. I mean, his papers are very careful.
Exactly. Yeah.
So no, everything is correct. And I met Peter in Marburg last year at the conference, and where I talked about this stuff, very fresh. And I asked him directly, why didn't he publish those papers? Is there anything wrong? And he said, well, small results, I didn't think it was worth publishing. Then I moved to other things, and I just, and then he told me that he's now encouraged to get those things published. Okay, but so maybe they will be published at some point. But anyway, that's okay, so that's what I will be talking about. We have our contribution in a way is that the role of the translation automorphs is made explicit. So they did not appear in the previous papers. Okay, so what are Hopf heaps? So this is the notion which Greenspan called quantum cotors. Okay, so in this world of dualizing things, what we see the quantum space is actually functions on a quantum space and so on. So this world there's really called functions on a quantum torsor, but called a cotorsor. Anyway, so let's go back to so I will use the term heap here, just not to confuse and not use co-heaps, which are also possible to define.
Mm-hmm.
Okay, so we start with a coalgebra. And why is it natural to start with a coalgebra?
So all this story about this cotorsor. So the idea of this definition is that the linearized Hopf is an example of this.
What do you mean linearized Hopf?
Linear space spanned by heap must be an example.
Yes, it is Hopf. It's a linear in the same sense as if you have a group, you can have either a group of algebra,
Linearize the group,
or the functions as a finite group functions on a group of algebra. So one is the dual of the other, of sense. So they took, rather than linearizing, they looked at the functions. If we think about functions on a heap and then write the axiom.
Yeah, but this is not this construction. This is construction of the linearized heap.
Linearized heap, yes.
Okay.
Yeah, linearized heap. Okay, so we start with the coalgebra, and as everybody knows, it's a natural thing to take a coalgebra because from the start of our education, some of us met sets already in primary schools. We were taught again according to the Bourbaki influence model. Every set is a coalgebra in a unique way. So we co-unitary coalgebra in a unique way. So we never mentioned this thing because there is a diagonal function and the function which goes down to a singleton, the unique function. They produce the structure of the coalgebra. So in a way, algebra is a linearized set, if you want to think about it that way. Okay, so we start with a coalgebra and then we have Turner operation on this. Of course, everything is linear, so the tensor product is over the field. It's co here means that I change the order. That's a
Co-opposite coalgebra.
or opposite coalgebra. Right. Coalgebra has only one structure, right? So why call it co-opposite? So co-opposite coalgebra is just a coalgebra. Anyway, okay, so it's a co-opposite coalgebra or opposite coalgebra. And right, so that's notation, but remember this is not there's a linearity built in, basically. Right, the first axiom, nothing new, that's the associativity, as in the case of Heaps. Well, the second axiom is if you write this axiom, it's multiplied A element was doubled, which means that we apply the diagonal map to this, which means that we need to apply the co-multiplication. And of course, everything has to be linear, so there must be epsilon, the co-unit. So multiplication is delta, co-unit is epsilon, usual notation. Ooh. Okay, amorphous of Heaps is a coalgebra map, right? Because the coalgebra structure is built in, which preserves this operation. And this Grunspan map is a coalgebra map, such that, as you can see, if I shift by one, in the as I explained, we have to the heap standard heap. We take the inverse in the group twice. This does not have to be identity, so we have this correction. Right.
Sorry, for an antipode, you can prove that the antipode is an anti-homomorphism, both structures, coalgebra and algebra. So why this theta is?
Because if you take an antipode twice,
so theta is twice.
You should think this, as I said, it's like taking the inverse of the inverse.
Ah, it's just, okay, it's a square of the inverse.
It's the square of the inverse.
Not the inverse, the square of it.
Yeah. Which does not have to be identity.
Okay.
So there is a correction, and in the examples there is a correction. Okay, every Hopf algebra is a heap. So to satisfy Tomek in the obvious where the and here the
theta is S squared.
S squared. Exactly. Okay, so now how about translations? Okay, so so this is exactly I'm repeating the same definition, but now linearized. So we have a linear map from C to C, defined in that way. Okay, so chi, remember, is the symbol for the Turner operation. Okay, and I call it a right AB translation. And so this is a vector space which is spanned by all those translations which we call ENC translations. But there is also a left-handed version of this. In the case of usual heaps, the left translations and right translations are, I don't remember, one is the inverse of the other, or something like that. So they are very closely related. So we just opposite product that you take. Here we can define, so I call them left translations. And the difference is that the argument sits on the right. Okay, so I'm translating from the left with A and B. That's why it's called the left translation. Here I translate from the right. Okay. Okay, there is no straightforward connection at the moment visible with this definition. But there will be some. Right, this is a heavy slide with some properties. So yeah, it's really heavy. Swidler notation and all that. Okay, so what is worth noting is, so if you apply delta, so this is just an element and you use this, the heap operation was opposite in the middle. So if you can see follow the indices here, 1, 1, 2, 2, but here is the order change with the indices in A, which just comes from the fact that I was co-opposite in the middle. Yes, the definition. Okay, this is one of the Maltsev identities. Okay, this linearized Maltsev identities, because this means that yeah, A1 means A2, and okay, you can reduce it. In this here, you can reduce it to identity, and this corresponds to in the usual case, if you translate by AA, then you will get identity. Okay, and there's a composition law, which I didn't write it for but that's what I should have written also for this. Is the same as for the standard heaps, when you can see that if you compose, you end up with a translation. Compose two translations, you end up with a translation. Now, if there is a Greenspan map, then there are more properties one can write. So, for example, one can interchange indices here. Swidler indices here was A1, A2, but we can swap them around and but use theta. Okay, the same thing happens here. So actually, this follows from that one. And okay, and if I look at there is a composition the other way around. Okay, but it involves theta. I want to. So I think Greenspan assumed that theta is an isomorph. It is bijective. Yeah, so if you think about theta being bijective, then of course you can remove theta from this side and put the inverse of theta on the other side. But we are not assuming bijectivity of theta. And I think the Scharenbruch did not assume bijectivity either.
May I have a question? Is it true that group-like element of this C is a heap in the usual sense?
Yes.
Okay.
But Mike, wait, I believe you mentioned that theta comes out as part of the structure. Now here you write if Greenspan map theta.
Yes, because I haven't proven yet that it comes out. So this will be on the penultimate slide. The last slide will be with references and
slide 68.
Slide, well, it's not a slide, it's how do I call it? Anyway, so first the translation of Algebras theorem that you can follow is that, and as you will see, I'm not assuming if that exists, purists. So translation is vector space, of course, which is closed under the composition. And I choose the opposite composition just to make the conventions right, because it's you have homomorphies acting from left and you compose them, then it's different than composing when you write the arguments on the left or an argument on the right. And so this is a convention that works. Okay, it can be written in a different convention. Some anti-algebra maps or the co-algebra maps will appear where they do not appear here. Okay, so this is just how the delta is defined for multiplication, and the epsilon is just epsilon of A and B of the translating points. If theta exists, then there is an antipode. and it has this form. So it's a Hopf algebra then. Now, if C and D is a morphism of Hopf heaps, then there is a morphism of bialgebras. So this reproduces the functor from heaps to groups. If we have a morphism of heaps, we could define a morphism of the translation groups. So here this translates into a bialgebra map, or Hopf algebra, if there is a Hopf algebra structure, which I will argue that there always is Hopf algebra structure.
Sorry, correct me if I'm wrong. If I have a homomorphism of, if I have a bialgebra, yeah, we recently had somebody saying the same. Please correct me if I'm right. Yeah, it would add up. Okay, so what I want to make sure of, but if I have a homomorphism, I mean a map, a linear map between Hopf algebras, and I know that this is a bialgebra homomorphism, does it imply that it preserves algebra? It does. Okay.
In the same way as for groups.
Groups, exactly. Just.
And essentially, it comes from the observation that the Hopf algebra is a unique antipode. So if you retract the antipode using the isomorphism, it just it has to be the only one. Okay, so with this we have a functor from the category of Hopf heaps to the category of bialgebras for Hopf algebras, as we shall see. I'm not if we have a Greenspan map, which always is there. It's the second paper of Peter. And we can state similar statements for the other translations. I will not repeat them. If I remember correctly, then there the composition is not the opposite composition. So. Okay, so that's again someone reading. Okay, so but this is if we have a group like X in C, in general, coalgebra does not have to have a group like. However, every coalgebra over a field will have at least one element with a counit is one, and this is important. Unless it is a zero. A zero. Okay, non-trivial card. Okay, so so if we have here, we have then we can define the multiplication well this way, and S of A. Well, just compute what it is corresponding Hopf algebra, and then there is an isomorphism between the two, left and right, and this is what happens in the. So that's why on the level of heaps, theoretic world, we don't see any difference between left and right translation groups. Okay, so next is called Galois coordinates. They are just like objects, but with code. So this relates to as I mentioned, the observation of Schauenburg that there is connection between heaps or quantum torsors and bi-Galois objects. Okay, so this is just a dualization of the notion of a Hopf-Galois extension or Hopf-Galois object. Okay, so there is a canonical. Maybe we should start with the canonical map. Okay, so first of all we have a module coalgebra, H module coalgebra. So just a reminder, this means that H acts on C, it's a module, a right H module, and the action is compatible with the algebra structure, like so. Okay, the canonical map has to be an isomorphism, it's a Galois condition, and the second condition corresponds to the triviality of the coinvariance. Okay, so kernel of epsilon must be equal to the whole coinvariance, so they become trivial, just the field. Right. Okay, left Hopf-Galois coordinate is defined symmetrically with the left actions. And if we have a algebra that is both left and right Galois objects with actions on C commuting, so we have a bimodule, H bimodule, not bimodule, then we have a bi-Galois object. Okay, so the next step is the co-translation. So co-translation map has to somehow be related to translations. As the name suggests, there are some translations here, translations there. It's not an accident. Okay, so it's the co-translation map is defined in this way. We have the inverse of the canonical map and apply epsilon. So this is a map from, go back, slides, canonical map inverses from the copies of C to C tensor H.
Sorry, now the name co-translation contradicts the fact that it's a linearization of the translation.
It is, but you know, it goes back to the mistakes made in youth.
Okay.
So if it's a wrong name, I'm responsible for this.
Yeah, because when you are doing it in Hopf-Galois, you use translation instead of co-translation.
Exactly, I use translation and then the name was spilled and there was nothing could do about it. We could ask Dr. Fu. Anyway, and travel back in time. But anyway, the key properties. So all those properties in the dual setup. So when we have a Hopf-Galois, in general Hopf-Galois extension, specifically Hopf-Galois objects, they have been described by Schneider in one of his well-known papers on Hopf-Galois extensions from the beginning of the 1990s. Okay, so what the properties are, that if so quite easy to derive, except for the last one. The last one requires some work. So if you apply epsilon with tau, then you get just epsilons. If you apply tau to A1 to A2, it's epsilon of A. This is just the inverse of the fact that tau is the inverse of the canonical map. Also, the next one also follows from this, and two-sided inverse, so you can use one side or the other side, and this requires some work. Okay, so what does it tell us is that the co-translation map is the anti-homomorphism of algebras, or it's to be precise, it's a well, no, I said it incorrectly. So here, yeah, so in other words, it's a homomorphism. Maybe it's a good moment to use the wonderful. I can write with my finger. Okay. So this, but I should change something. Which one I should?
No. Oops. You have to press. Press on this arrow above a plus. Yes, and here, yes. Now you're right.
Okay, so tau is a map from C tensor C to H, right? But this axiom tells us I should use this then. The last axiom tells us that actually this is co-opposite in the first leg. Okay, so now this is a homomorphism of quadrants. Then I press what?
This, yes.
And this condition is quite important, plays some significant role. Okay, so now what we can define is a subspace of C tensor C. Okay, so far it's just a subspace. which is some sort of invariant space. So on one hand, we have, well, the action with tau. On the other, this action just kills C, replacing it by epsilon. Now, using the previous properties of the co-translation map, one can prove that this is a co-ideal in this coalgebra. And as you can see, this call here is important because this is in the middle. We have the first term of tau, so this changes the order. That's why it's multiplication has to be the opposite. Of course, in the case of set, we don't see it because the diagonal map is commutative or co-commutative or co-co or whatever. How many co we want will be satisfied. Okay, now, as I mentioned, we are working over a field. So in C, there will be at least, well, this set is non-empty. Okay, the inverse image of epsilon of 1 under the epsilon is non-empty. So we pick one element. And what we then see is that actually delta, if we take so what I wrote here. So this bar means that I'm now using the cosets, right? So in the quotient space. So this quotient space can, the quotient space, the coproduct of A is the same as the coproduct of A corrected with the epsilon. Okay, the next step is just so it's a dualization. It's again it's a thing that was defined in dual setup by Peter Schauenburg. It's Ehresmann-Hopf algebra associated with a Galois co-object, Hopf-Galois co-object. Okay, so we take this quotient and it turns out to be a Hopf algebra. The identity is this E is any chosen element in there. Of course, doesn't matter which we choose, because if we choose a different one, then there is a correction of epsilon on this other one.
Sorry, just to make sure I understand you correctly. Here I have like parentheses, right?
Yes.
It's not C.
Yeah.
Okay,
Okay,
yeah.
And sometimes we are swapping these tensorons. Previously it was CO tensor C. Now is
good points. Good points.
We've got you. 1-0.
I knew this would happen.
Pretty good.
And I'm sure that Małgorzata is now smiling. But
Yes, did you see it on her picture?
there's a secret reason for this, why she's
Okay.
Anyway. And also there is an antipode. Okay, so it's a Hopf algebra. So with every algebra, with every Hopf-Galois object, we have associated Hopf algebra, and this it just repeats the individual picture what Schauenburg did in the Hopf-Galois extension picture. Okay, and so this follows from the properties of the co-translation map.
If it wouldn't be an object, it would be a Hopf algebroid, right?
It depends what you understand by Hopf algebroid. It would be a bi-algebroid, or it would be precise. I think it would be co-algebroid in the sense that the base is not an algebra, but it's a co-algebra.
Yes. That's a good point. Yes.
But what is the Hopf in the algebroid case? Well,
Yeah. It's tricky.
it's tricky. I think it will be in the algebroid or Hopf algebroid in the sense of Schauenburg. So there would be no antipode, but sort of canonical map would be invertible. So what he called crossed Hopf algebras. But it's recorded, so perhaps I shouldn't say.
Yeah. Everything you say can be used again.
Exactly. That's evidence. Right, so now a theorem. From heaps to Galois objects, if we have a Hopf heap, then C is a right Hopf Galois object over the right translation of algebra. So we have this, I call it Hopf algebra, but it is a bialgebra. But still we can define the action, and the definition does not involve the antipode. That's the action, okay, which is just given by the translations, evaluation of the translation.
What is the reason for writing this first as a right action and because the tau BA now you are regarding as what? It's automorphism.
Okay, so that's the definition of tau, if you want. I just reminded you the definition of the tau.
Okay.
So in other words, it's an evaluation. The action is by evaluation. Yeah. Yeah, that's the point. So the tau AB is a function, it's a linear transformation, and you evaluate.
Yes, but automorphisms act from the left.
Well, they are not automorphisms.
You have to invert something.
Well, that's why there is an opposite multiplication, perhaps.
Okay.
Entering. So I wanted to. There are four different sides with which you work, and at some point you make a wrong choice or good choice. I don't know, traditional choice, less traditional choice. And in the audience of 5 people, at least one will not be satisfied with the choice you made. But anyway, that's the next thing. One can calculate what the Ehresmann of algebra is. And this is this.
As was to be expected.
Yes. But I use so what we deduce from this is that the thing on this side, you see, if I look at those things here, they do not use the antipode of H. Right? I define the antipode on the quotient with the on the other side.
Are you are using this co-translation?
But I'm using the inverse of the canonical map, but in the inverse of the canonical map and the previous, the axioms that I wrote, I didn't use the antipode at all. Not the axioms, but the co-translation. There is no antipode. Okay, so this.
Sorry, is it related to this very well-known fact about Hopf algebras that the canonical map of the Hopf algebra is invertible if it's a consequence of the
yes over the category, exactly. So we can think about this equivalent definition of a Hopf algebra. It's bialgebra such that it's again one of the Schauenburg papers. The bialgebra that means Hopf Galois extension is a Hopf algebra.
At least if you are over a commutative ring over which everything is faithfully flat.
Yeah, faithfully flat here. Okay, so in this case, as a consequence, we learned that actually the name, this translation thing, okay, I call it Hopf algebra translations. It is a Hopf algebra. Okay, and then you can do this on the left-hand side as well for the left translations. And then you discover that you have a bi-Galois co-object. Okay, and then the last, I already mentioned this, these two guys are Hopf algebras, so you get the antipodes. If you try to write what the antipode is, well, it requires some effort, and time depends on how strongly you pray and fast, and at the end you get the answer. Okay, so a bit of the proof. So what is the canonical map here? Well, it's sort of obvious, with the obvious misprint, which would be C2.
Oh, yes, of course.
And this is the inverse. Okay, the inverse uses the translation as well. And then you just discover what the co-translation map is. Well, it's actually the translations. So the co-translation map assigns translations.
So Tomasz was right.
Yes. Is he ever wrong? It's not only your privilege, Piotr. Okay, the isomorphism between the Ehresmann thing is this one. Okay, but of course there is something that needs to be proven, because here we have a class yes, and here we have this depends on A and B, so it requires a few steps of proof, and it essentially uses the properties of the left translations. So I displayed the properties of the right translations and the list of them, and then you have a similar list from the left translations, and then when you use to play with those properties, you realize this is a well-defined function, linear transformation. Okay, so after the prayer and fasting, you get the value of the antipodes. And again, E does not depend on the choice of E.
Yeah. So your previous definition of this antipode, the original one, contained this theta.
Good point.
Yeah. Now
it does not contain. So then we ask Peter Schallenburg for help in the case, but I don't know how many slides I need to go down to ask him for. Okay, so but before doing this, I will show this goes the other way around as well. Okay, so if we have Galois co-objects, then we can construct heaps. Okay, so I denote this action here, the operations, so not an action, the operation of the heap operation, referring to C and H, and there is a reason for this, because it's data here. I don't write all the data, but so we have a Hopf algebra and the right H Hopf Galois object. So in particular, we have the translation map here. So we can use it to define a Telmer operation. And using the properties of the co-translation map, one easily checks that this indeed is a heap operation for a Hopf heap. And again, note this code here. This comes from the fact that in the first leg of the co-translation map, you have the opposite multiplication. Okay, and then what you discover is that actually the H you started with is isomorphic to the translation Hopf algebras. Okay, so everything somehow matches together. It's sort of you go one way and you end up with something which you started with. You recover what you started with. If you go the other way, you also get back to what you started with, up to isomorphism.
So sorry, can you go back? Because here comes the theta, right? No, where is it? I thought I saw theta somewhere here.
Yes.
Where is it?
It's not yet written.
I saw it Grunspan. Okay, and okay.
Okay, so it's a Hopf heap with the Grunspan map. So the heap operation is here.
Yes.
The Grunspan map will come later. Okay, so I want to explain. Okay, I hope it will come later. Or it's something a posteriori, perhaps. Well, I don't remember exactly what I wrote in the slides. Okay. Let's see.
Thank you.
The isomorphism and its inverse, so it's just for the record. Okay, it's a sort of obvious ones. You have tau AB, so you use all the letters that you have, but rearrange them, and it works. And in the opposite direction, you start with an element of H. You have your chosen element with the counit 1. Again, this does not depend on the choice of the element. It's property of the of those translations, and then you act, so just reuse what you have in your disposal of the object. Okay, and for the interested, there is a Greenspan map, and you can calculate this out, and it looks like that. Okay, so we have a sort of one circle, because it suggests that there is a vicious circle somewhere, but it's just, we have sort of path from co-Galois objects to or Galois objects, wherever call sits, to Hopf heaps, from Hopf heaps to Galois objects. If we start with the Galois side, okay, if we start with the Galois side, we get the Greenspan map in addition. If we start from the side without the Greenspan map, we still have, so if you, again, I will go back to the slides. Okay, in those statements, points of the proof. I didn't use the, so it's a Hopf heap. I didn't assume existence of a Greenspan map. Okay, so I can do all this, or we can do all this without assuming Greenspan map. Not needed at all. But if I go in the opposite direction from what I started with, I will get the Greenspan map. Okay, so that was the punchline of the second of Peter Scheinberg papers, that every Greenspan torsor will have a Greenspan map. Okay, so in fact, this is what I've done so far is a categorical statement. So we have an equivalence of categories. So first, I define a category of Galois objects. Okay, so these are pairs, and of course with all those other data, actions, multiplications, everything there. Okay, CD are coalgebras, HK are Hopf algebras. And what we want is, as a morphism, we have a pair. It's a homomorphism of coalgebras and the homomorphism of Hopf algebras, and some sort of compatibility with the action. And if you have we change the base or whatever the acting object, then you also need to take this into account in the preservation of action.
Equivariance.
An equivariance, yeah. And here are the functors. Okay, so this I haven't maybe. These are Hopf heaps, HH. HG are Hopf Galois co-objects. So Hopf heaps, I already defined what the morphisms are. And the functor takes, assigns the translation of algebra. And this is functor that I've already described. And in the opposite direction, we associate the heap. And we just forget about G. Okay, so these two categories are equivalent. And if I compose helium with whatever it is, Ga, gallium. Then we get the identity. And if I compose this other way around, then of course it's an equivalence, so we get an isomorphism. But on one side is an identity. And this reflects in a way what's going on the level of heaps and groups. Because if I describe this way of retracting a heap to a group. So when we start,
It is done.
Thank you, chemists.
Gallium and helium.
Okay, so if we should have published this in chemical letters, something like this. Anyway, in the joking apart, the serious matter, if you have a heap and retract it in a point to a group, okay, then what you do, you have a group, so you can associate to this a heap by taking the inverse the ternary equation. You end up with your original heap. Exactly. There is no up to anything, just on the nose. If you start with a group, convert it to a heap, then you will have a freedom of choice in your elements. You can choose a different element than the original neutral element, and then you get a different group, but it's an isomorphic. So it's if you combine those functors one way, or those operations are not a functor because you are choosing an element. So you get to the translations, you have a functor. One way you have an equality, and the other way you have up to isomorphism.
Sorry, if you have two different points of the orbit, then stabilizers are not only isomorphic, but they are isomorphic up to conjugation. So can you say something more specific about yes, about this isomorphism?
Yes. So that's in a way exactly what happens. So this isomorphism is given by those translations. So this conjugation is encoded in the translation. So essentially what you do, you translate the neutral element from the bad one to the right one. Okay, so it's a very specific isomorphism. It's not just any isomorphism, but a very specific.
Tomasz, would you mind reminding me this chi CH is that's how you create a heap, right?
Okay, so the heap is you have a co-translation map.
Yes.
And then you act with, so you have three elements A, B, C.
Yes.
You act with co-translation map on B tensor C and act on A. Okay. Because the co-translation map is in H, so you can act from the right.
I've got you. Thank you.
Just exactly as I at some point I mentioned how you get a torso, so free and transitive action of a group of translations on the heap, and this was exactly the same process.
Yeah, linear.
Okay, so this is the, I said penultimate slide because it is, although it says 66, which is a good number for various reasons. 1966 was a very important year. England won World Cup in football, the first and last and the only time ever. Okay, anyway, but as a proud Welshman, I'm proud that they have never won it again. But so that's the conclusion. If you put together those quite convoluted arguments, then you will see that every Hopf heap admits the Grospan line, just as in the paper of Scheinberg. So it's a known result, but Peter nor what was the first name of Grospan?
Oh, I don't know.
Yeah, I've never met him. So they never used this concept of translations. It's a Hopf algebra of translations associated. Okay, so the last.
So your result is not on about the existence. It's realizing this
Realizing this, yes.
via this
Via
translation.
the Hopf translations, yes. Okay, so as I said, this talk is based on my paper with Małgorzata. Thank you, Małgorzata. And the next reference is for Hopf Heaps. So the Cyril Grunston. Now it comes back. You see the initial Cyril Grunston. Okay, so quantum torsors, journal Pure Applied Algebra, back in 2003. Peter Schauenburg, then 2 unpublished papers. And there is another paper which starts mentioning heaps in this context by our good friend Zoran.
I just met him.
You've met him.
Just a few days ago.
You see. It's a pity he didn't stay.
No, I met him in Bologna.
Somewhere else. Okay. Right. And the key steps of the proofs are actually based on other papers by Peter Schauenburg.
But for a change of published.
For the change, they are published, yes. And also they are on archive.
But wait, so what is Zoran doing with heaps? Cups.
Cops.
These are not cups, okay.
Not in the sense of the, it has nothing to do with the authorities here.
Okay. Hippie categories. So he's a hippie.
It's a hippie category. So in recent years, I've done quite a lot with my collaborators, Simeon Dras, Bernard Rybowowicz, Paolo Saracco, studying these kinds of categories.
Bernard, I think, is here.
Better be. He said he would be. Anyway, where the hippie category is sort of going from abelian categories, the category of heaps, of abelian heaps is not an abelian category. Because the sets of homomorphisms are not abelian groups, they are abelian heaps. Then you end up with a sort of hippie category in which some interesting things happen, such as the things that we don't normally realize, that the finite product of abelian groups and the finite coproduct of abelian groups, they coincide. The finite product of abelian heaps does not coincide with the finite product of abelian heaps. So at the next step, if you try to look at the problems of, projective objects, you have no splitting of sequences, right? The notion of an exact sequence stopped making sense. There is a bar exact, so there is some sort of categorical correction with the exactness. And if you are interested in this,
So some kind of homological algebra makes sense.
yes.
On the level of bar exactness.
If you are interested in this sort of categorical approach, so there's nice work of Alberto Facchini, properties and realizes. They are not called semi-abelian. There is some name also for those categories. I don't remember. So Zoran was looking at this also from categorical perspective. It's a short, you can see 8 pages or 9 pages.
But how are quantum heaps related to Hopf heaps? Is it the same thing? Or?
It's the same thing. Well, or the dual, yeah. I don't remember exactly the setup. Grunspan considered both. So he defined torsos and cotorsors. There is a sort of last section or appendix where the thing is written for the dual picture.
But the equivalence categories works only for cotorsors, not.
No, it will also work for torsos. Okay, and essentially it's almost 1 hour 30 minutes, 1 hour 25 minutes. So let's stop now.
Thank you so much. Okay, plenty of time for questions, but Tomasz, can you remind me when we were choosing a topic for Tomasz to speak about? And we were looking at his paper with Małgorzata. I remember our discussion where he said, aha, so he does it for co-objects because he cannot do it for objects. This is what is stuck in my memory. That's why I asked this question.
No, because he couldn't.
Because this is the
Parallel theory.
yeah. It's
Can you go back to this equivalence category slide, please? Okay, so that's claimed for Galois co-objects, and you are telling me that I can do it much in the same way for Galois objects.
So but you have to work out what the translation of algebra is, but what Greenspan and Cyril and Peter were doing, excuse me, this was done for the Galois object side. So you had Galois, bi-Galois objects. Peter had bi-Galois objects, so that's yes, it's all can be done, but I mean, this we haven't looked at the which picture is dual. The original that they consider is dual, or this is dual, whatever. We didn't look at the original version, but I don't see any obstacles to for this.
The same diagrams.
Yeah, the same
arrows reversed.
Exactly.
So here your Hopf heap would be a linearization. In the sense, algebras linearize spaces, you linearize the usual heap. Sets, yes. You linearize the usual heap to a Hopf heap.
Yeah.
But now, if you would try to do all this equivalence game with Galois objects, then you'd have to have function in the heap approach.
So this started, it might be that it will not work. Sorry. Might be. Now that I think about it, because at some point it's
And that's what we discussed.
probably you are, Tomek, when you're discussing, you're right. So as I say, we didn't look very carefully on the other side because we wanted to start with the very classical picture when we think about the set as a coalgebra and define the structure on it.
Yes.
And but it might be that at some point indeed there are functions on something, and then you need finiteness condition at some point.
No.
But if
No, there are algebra morphisms. You are speaking about not of sets. Now you are speaking about algebraic.
Yeah, but those things, don't forget, they are of algebras. So if they're duals, I don't know, maybe you need to take dual of them.
No. It's about categorical statements, and the category of algebras is self-dual. If you take the axioms,
Yeah, that's true.
everything arrows,
That's true. So
everything's the same.
that's true. But how do you define the dual to this?
Dualizing all diagrams. If you write algebraically something, okay, you have this Sweetler symbols and so on and so forth.
Yeah.
But if you draw a diagram, it's very easy to dualize it.
Yeah, that's true. But
A dual of an algebra is not necessarily a algebra.
exactly.
No. It's not the dualization in the sense of linear dual. It's not a dualization in the sense of Hopf dual. It's a dualization on the level of categories.
Yeah, on the level of categories, it will work.
Categories, yes.
That's right. On the level of categories, I agree. But this is when you come to
But you have to a notation.
in the level of categories, you have objects and morphisms, but you don't have elements of your objects. And the elements can, how you want to describe this elements.
If you play with diagrams, you can forget about elements.
Yeah, but maybe still, if you just do this categorical view of this opposite category, maybe you will not get after all this picture of functions on a heap.
No. Then you are defining algebraic heap.
Yes, exactly. Yeah, so there is, so that is the problem, yes, okay. I'm happy, I'm happy. So any other questions or comment? Maybe how about Małgorzata, would you like to comment or weigh in? No, she doesn't.
I haven't any comment.
Okay. No comment, okay. Anybody else, any questions or comments or suggestions or complaints or applauses?
I would.
Yes,
Yes.
Maybe I just missed it. Is a heap the same thing as a set with a free and transitive group action?
It is, yeah.
Okay.
Or it is the same, if you can say it's the same as well, as a system consisting of a group and a subgroup, and you look at all cosets. Take any coset, it will be a, yeah. So it's in a way, it's a torsor in this sense, or it's a affinization of a group, if you like.
How much you wanted?
Yes, so I would have a question about passing to this quotient, going to this homogeneous space. Okay, so it's a case of an action which is not free. What part of this theory can be extended to the context of general actions, not necessarily free actions?
I'm not sure.
Because if you have any action, any action
It's
is
the union on the classical level. You have a
the
group,
union of.
you are living the world of groups and sets and actions and so on.
I would like to even understand the situation on the classical level.
Yeah, on the classical level.
Yes, sets with group actions.
So I think you will miss some of the axioms because if you put, so there are things which are called generalized heaps. And there was a mathematician called Wagner, he wrote a number of papers on generalized heaps when you, so for example, heap captures the structure of a group in a way. So if you have a retract, you have a group. If you drop the axiom, but the group comes from those Maltsev conditions.
Yes.
This is really, yes. And where the freeness, exactly, where the freeness sits. Now, if you drop those axioms, then you are not able to derive the middle, the shifting by one. So what people do, so you don't capture a semigroup. You don't have the associativity, the semigroup associativity. So what they do, they impose, this was, I think Wagner was the first one doing this, you impose this condition with the shifting by one and changing the order of elements in the triple. So maybe I should go back to the, how do I go quickly to the quick way? Or should I go to the page?
Wait, number one. Type one.
But I can type, he cannot.
He cannot write.
So that's the definition, right?
Okay.
Okay, so you can, those generalized heaps, you remove this axiom, right? You have this, but you add that.
Okay.
It can no longer be deduced.
It can no longer be, without this axiom, you can't deduce this one. So you replace this one by this associativity. But then you don't get semigroups, but inverse semigroups.
Nice. Yeah.
Nice, let them group, but it's not, so there is, as far as I know, there is no generalization of Heaps. Maybe Bernard can correct me because he studied physics there. There's no generalization of the heap which captures exactly semigroups.
Yes, Bernard?
There is no, I don't think there is something like that, yes. So you can go one way from semi-heaps to semi-groups, but not the other in obvious way. You can have multiple different semi-heaps which might somehow give you the same semi-group for a particular choice of elements, something like that.
Okay.
So there's no equivalence.
Yes, there's no equivalent. So there's
Mhm.
so the
And-
dropping. Yeah.
Sorry. And also here you can always go from heap to group and go back to heap. To always come back.
Yeah.
So it's much more complicated.
Tomek, are you happy?
So
Okay, so I will have another question.
Cannot.
If you have,
so before you say your question, because I just wanted to comment about not giving the answer to your previous question.
okay,
So this reminds me, you see or just comments. I mentioned this that in the affine spaces, if you drop Maltsev identities, with Maltsev, no, the abelian property, yes, you drop you see that there is no triangle axiom.
Yes.
But triangle axiom, you drop also something else, which I don't know what it is, because it's a so, I haven't thought about it very carefully. So it's you lose a triangle axiom at something and something else, not just one axiom. And here is a similar situation. You drop this, and you
are losing more.
you're losing more. So this definition is quite rigid. If you try to remove one part of the axioms, then you lose more than you wanted to lose.
Yeah.
Go on with your question.
Okay, so my next question is about thinking about these things as orbits. Okay, if you have an orbit, okay, you could think about a resolution of this action, of this orbit, in terms of the action group point. Is there some relation between theory of group points and these heaps?
I think that there must be, but I there must be a relation.
So Piotr's first question was very natural.
Yeah.
Mhm.
Okay.
So if you have this resolution, then you can, in a sense, continue it to obtain some simplicial object. And
Yeah, I mean to say, it's if you think about the geometry.
can you construct some simplicial object from a heap, like for the groups, for instance? Can you construct something like BG, an analog of this? Okay.
As I say, this is not I mean, it's not even the case of abelian heaps. It's not an abelian category, and various homological.
No.
I know. I'm
talking about simplicial.
Yes,
About the BG.
I don't know. I simply don't know.
Okay, so next question, very natural question would be, okay, regarding heap as an algebraic structure, some kind of algebra, okay? What are modules for this algebra? What are actions of heaps? Can you speak about some heapy action?
Actually, can. Bernard, can you help me?
Bernard?
With which one?
With the heapy action, but it's like groups act on sets, heaps acting on sets.
I'm not sure if the action should mimic the action of a group on a set. But if you have some algebra whose axioms can be modeled by some how it's called operator, you can linearize partially these axioms to get the notion of a module or a bimodule. Okay.
So again, this is a very good question, and I don't know the answer.
So this definition, I suppose, is operatic. It's a non-symmetric operatic.
It's either operatic or is cooperative or what is.
No, it's an algebraic structure.
Yeah, it's an algebra.
There must be some opera.
I remember Lode was looking at operas.
Yes.
But you know, if you think about the group actions, then the action of a group on a set, you start with a set and you look at the map, well, group homomorphism on a group to the automorphism
Yes.
of the set.
Yes,
Now the automorphism automatically become a group.
Yes.
It's a distinguished element,
yes, identity.
identity. So
So the question is, do you have something like automorph, maybe not automorphism, something like
okay, so we have
an analog of automorphisms in this context?
okay, so yes,
I have some object and I can speak about heap of some heapy symmetries of this object.
okay, so the corresponding thing is it's a holomorph.
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 So holomorph is a
Sounds like alien.
well, not, it might be alien to you.
It is, I'm sure it is.
So if you have a group, okay, then usually we associate to this an automorphism group. But automorphism act.
No, I was not speaking about this. I was speaking about a set and a monoid of endomorphisms.
Yeah, so but now about automorphs, I just wanted to finish so that you have, I never remember which way. Okay, you can form
Inner automorphisms. Yes.
automorphism, and then there is you have it's a group. This is called holomorph.
Ah,
Now, if you have a heap, if you have a heap like this, then, of course you can consider endomorphism of heap. This is a monoid
yes,
with respect to
composition.
composition. But also this composition distributes. So in the case of an abelian heap, just like the abelian groups rings, endomorphisms of abelian groups are rings, every ring can be realized as embedded in something like this. So if you look at the end of the endomorphism of a heap, the endomorphism of an abelian heap, well, you compose them and you get an endomorphism, and you have the distributivity, or you can define a Turner operation, a heap operation on the endomorphisms. Because it's a category of abelian heaps is a heapy category in the sense that homomorphisms from one abelian heap to another heap will form a heap. Just like homomorphisms from abelian group to abelian group will form an abelian group, and it's a pointwise composition. So it's exactly the same, and the composition distributes over the Turner operation. So what you get what we call the truss. You have a monoid by a heap, which is also has a monoid on it, or the semi-group operation, and there is distributivity of the semi-group operation over the heap operation.
Okay, is the action of scalars, find space,
Is the action of scalars.
the scalars, lambdas,
Yes.
on the vectors for a given affine space, a representation in this sense?
It is.
Okay.
And so what I just wanted to finish that with this holomorph, that this is actually the same as automorphism of G understood as a, I don't know. Here as a heap. So the holomorph of a group, which is traditionally defined in this way, it corresponds exactly to this heapy point of view on groups.
And it is copy of G. Probably there are these translations embedded in this automorphism.
Exactly.
Mhm. Nice.
Okay.
I find.
Anybody else? Someone just had a heap of questions. It's, you know, anybody?
The herd of members of the audience.
I was like a gunman.
Anybody else from the Zoom?
From the heap.
I know, Adam. Adam, you are so silent today.
No, I don't have any question, but I very like the comment about hippie action.
Okay, if there are no further questions.
Because you know, we working of Heaps are just hippie people.
Exactly. Yes.
Exactly.
Okay, if there are no other questions or comments, let us think
Maybe one more. Can you twist heap?
and shout.
What?
For instance, for Hopf algebras, you can have some
Like dreams.
some twisted versions, some braided versions. Can you do similar things?
Well, the braided versions, yes, you can. So
Mhm.
why not?
So in particular, I can speak about this Hebbian condition, because it's about. Can you have something which is braided instead of being Hebbian?
Well, for the
Automorphism.
it's like that. I mean, you can define, I guess, you can define those axioms in a braided monoidal category.
Mhm.
And there is nothing that prevents you from writing these conditions. If you have a monoidal product in your category.
Yeah, but the question is whether still you have this equivalence between Hopf
Of this I mean,
objects and then.
I think you would need more conditions on the braided category.
Mhm.
It must be pretty close to the vector spaces, symmetric and vector spaces.
So it would mean that you cannot make it braided.
Well, you can. I mean, it's just like with the Hopf algebras, you can make the definition in the braided monoidal category, no problem. But then when you want to reproduce some of the results, then you have conditions on your category. Not all results will reproduce. Specific results about Hopf algebras, about specific Hopf algebras. Here we are talking about.
Yeah, but I'm interested mainly in this equivalence theorem between Galois objects and these heaps.
Okay,
so that braided version could make sense.
Well, it would make sense, but you have to be very careful because even in the unbraided world, if you replace the field by a ring, commutative ring, then faithful flatness is needed at some point. So to derive those results, and then then you have to restrict your category in some way. It becomes tricky. And if you just have braided category with no adjectives, then something is missing. Just like the theorem about the existence of bases in a vector space, which is essentially what you need faithful flatness for.
so in this equivalence, phase of flatness plays a role.
Yes.
So, if you forget about the field, you have some arbitrary commutative ring, let's say, you could linearize them over this ring. You could obtain heaps which are not isomorphic to
Well,
Galois objects.
I don't want to make any decisive comment because I haven't looked at it. But from the experience of working with over the rings, then at some points there are tricky conditions which are easy to miss, which I know from, for example, from the longish erratum to my book, with Prifysgol, we missed some, although he is his whole life, academic life, was dealing with rings and properties of rings and categorical properties of modules. There were some small things which we missed. So I don't want to make any decisive statements. I would need to go through the proofs and see in which places one can drop the assumption that we are doing over a field. I haven't looked at it.
Yeah, but what is your impression? Are heaps more general than Galois objects, or Galois objects are more general than heaps? If you do not impose these conditions on coefficients.
Okay, so going back to heaps, I feel more. Well, they are closely related to groups and also the torsors, and transitive actions of groups on sets. They are more general. Heaps are more general in the sense that you don't need to specify any elements. So. So what I mean by this is that this is a very minimal structure. This is the simplest definition of something which is writing inside groups or a bunch of groups, which is actually does not specify any elements. I know that one can write the group axiom as a one, the universal algebra as a one long term, which I don't remember, 27 or 127 terms. It's possible to write, to hide, to have a group hidden in such a definition, but this is unworkable. This is a workable definition where we don't specify anything. And now the time is over, so we can talk about philosophy. I mean, the colleague of yours, Janusz Grabowski, he did, at some point, he was working on what is called Tulczyjew program, right? Which is to replace, to find a description of mechanics without frame of reference. Okay, and what they observed, Tulczyjew observed, and then they followed with Kasia Grabowska and with Mariusz Urbański, was that what you really need to do, you need to get away from vector spaces, work in affine spaces. Because your Euclidean space in which the motion happens is affine, an affine space. And if it becomes a vector space once you have an observer, and you decide, well, I'm sitting there, this is my frame of reference, so I refer everything to this in the vector setup. So the heaps are doing groups and without referring to any frame of reference. So in this respect, it's more general. Now, whether you can get more general results, I don't know. But one thing that we observed working with those trusses is that there are more trusses than rings. And this is a very simple replacement of one of the axioms when we replace the abelian group by a heap and then homomorphism of groups by homomorphism of heaps. So, I think on the we in one of our papers also the Bernard and the Fleszard and Andruszkiewicz from Białystok, we classified all possible trusses. So the theory, in every truss you will have a ring, just like in every heap, you will specify an element, so there is a sort of retracting process. There is a sort of embedding, just like you can take a heap and you can embed it and view it as a coset of as a particular coset. So all those processes work, and they can be used. And so if you look at all possible rings on the cyclic group CP plus CP. Okay, so 2 copies of P is a prime number. Then you will find that there are 8 non-isomorphic rings. Okay. Where by ring I mean ring about not necessarily with identity.
How many trusses?
23.
23.
It's not a huge number, but
Bigger than 8.
non-isomorphic. And so some of them, if you look at the retraction, they collapse to those. They have to collapse to 8.
Yeah.
But they coincide at some points. So it's so I guess. But it's a philosophical issue, I would say. But do we want to complicate? So going back to Janusz and Kasia.
No, I want to simplify.
Do we want to complicate the description, or do we want to to simplify but pay a price for this? That you have to describe what happens when you move from one frame of reference to another, or some sort of what is called Galilei principle or something, what happens in inertial frames. So you have one frame, another frame, and you can translate from one to another, but you need to know what you are allowed, what kind of translation from one to another you are allowed, or you just live in the frameless world, but some things might get a bit more tricky.
Can you use this notion of heap to do something in the spirit of Cartan differential geometry of moving frames? For example, the notion of Cartan connection was invented to speak about things we are talking about in mechanics, for instance.
I don't know. Maybe Janusz would be a good person to ask about it, but here is a warning that the description of a fine space always refers to a vector space. So, so I think the program was. I mentioned this. I talked about things arising from the 3 brackets on the fine spaces they defined in Białowieży, the conference, and Janusz was there. Kasia was also there. So I was very careful what failed, but I think the program failed in a way. So from the philosophical point of view, you want to do things without a frame of reference, but in your whole language, you build a frame of reference. Because the fine space is defined in their view as there's also this reference vector space. So you have a reference frame. So they didn't use heaps.
Yeah, exactly.
But if you use heaps, you get away, you move away from the linear.
They can save their program.
Well, it's a huge and beautiful program in the sense that they studied bundles with affine fibers and very nice things. There's quite a huge. They developed quite a lot of geometry, but always referring to embedding this in a vector space, a vector bundle, or referring to underlying vector bundle. So there was
Okay. Okay, I think it's really time to wind it up and thank Tomek again for that. Thank you so much. Morning.